Okay, here we are on Polygons on page 13. Better get that guy up there. And we're supposed to find the central angle, interior angle, exterior angle, and sum of the interior angles. So we've got all of these different angles to find of the following regular polygons. Now, this is the big key in polygons. We're dealing with regular polygons. That means all the sides, all the angles are the same, which means we're going to be able to break stuff up into triangles and then solve them with stuff we know how to do. If it's not a regular polygon, we really don't have a lot of information unless they tell us exactly how big the sides are and how big the angles are. So let's start off. Number one, a pentagon. We can draw this one, though we won't need to do it for all of them. But let's say we have a pentagon here, regular, all five sides and angles the same. The central angle, so starting from the center and going out like this, well, notice how many there are. There are going to be 5 of these angles, and altogether is 360 degrees. So here we're going to do 360 divided by 5. We punch that into the calculator and we get 72 degrees. All right, the exterior angle. This is a little bit different. Here you're extending these side lengths and looking at this angle right here. So these are the exterior angles. So we have, how do we do that? Well, if you look, if you're walking along here and then you turn that much and then you walk along here and turn that much, by the time you get around to the last one, you have made a complete 360. So here we're going to take 360 divided by 5, just like we did the central angles, but for a different purpose. And 360 divided by 5 is 72 degrees. Good. The interior angle. Now this one is this angle right here, the interior angle, and you can see that the interior and the exterior are supplementary. So we're going to take 180 minus the interior angle. So that's 108 degrees. And the sum of the interior angles, we have 108 times 1, 2, 3, 4, 5. There we go. So that is 540 degrees. Good deal. Number 2, hexagon. Let's draw this one out as well because these will be a little bit tougher, but we can draw a hexagon, right? There we go, close enough. So central angle, again, is going to be like this, and you can see we've got 6 of them. So 360 divided by 6 is going to be 60 degrees. Now the exterior angles, change to that color, you'll notice it's going to be 1, 2, 3, 4, 5, 6. And yeah, we're going to take 360 divided by 6 again, and that's going to be 60. So these will always be the same, the central and the exterior, for 2 different purposes. One, you're going around 360 in the center, and the other one around the outside. Now the interior angle, we're going to take 180, subtract the exterior angle. So we get 120. And when we add all of them up, we get 720 degrees. That's a total of the interior angles in here. Alrighty, so let's do this last one, well, number 3 with the heptagon. So this is going to be 360 divided by 7. That's going to come out to be a decimal, so let's go ahead and punch that in, 360 divided by 7. And that is 51.43, so 51.43. And we know the exterior angle is going to be the exact same thing, 360 divided by 7. Then the interior angle is going to be subtracting this guy from 180. So take 180, subtract that guy, and we get 128.57. And then the interior angle, so that's that one right there, we're going to have 7 of them, so we're going to times that guy by 7, and we see 900. There we go. Now notice this, we're going up 180 degrees, up 180 degrees, and that's exactly true. This is actually 180 times 3. I'm going to write this down. And this is 180 times 4, and this is 180 times 5. Yeah, so that's kind of this neat little pattern, and that's exactly what's going to happen. This is going to be an octagon, 8 sides. This is going to be 180 times 6 to get the sum of the interior angles. And in general, the formula is going to be 180 times the number of sides minus 2. I want to go through a little bit of a derivation of how this happens. To get the exterior angle, we take 360 divided by the number of sides. And to get the interior angle, we take 180 minus that. And then, so this right here is the interior angle, and we times by that, times by the number of sides, and we get the sum of the interior angles. So if we jump this in, we get 180n minus 360, and the n's cancel. And then we can see, oh yes, if we factor out 180, n minus 2. So this will always happen no matter what. Here's the exterior angle. Here is the interior angle, and then that would be the sum of the interior angles. So yes, there is a shortcut way to do all that. Let's go ahead and march through these other ones then. So the central angle, we're going to take 360 divided by 8, that's 45 degrees. So that's what this one is going to be, exterior angle. The interior angle is going to be 180 minus 45, that's 135 degrees. And when we times it by 8, it's going to be 180 times 6, which is going to be 1080 degrees. All right, the next one, nonagon. So 360 divided by 9 is 40 degrees, so that's going to be there and there. Then it's 140 degrees for this, for one interior angle, and then times that by 9, and we get 1260. And notice that we're still going up by 180 degrees each time. All right, for the last one, I'm not sure I'm going to be able to do it all in my head, but let's try it. 360 degrees divided by 36. So the central angle, each side only gets 10 degrees on it because there are 36 sides out there. And then the exterior angle is going to be 10 degrees. And again, I just draw a couple of these. It's like this. So this is going to be 10 degrees, and then that's going to be 10 degrees, and then as it turns again, that's going to be 10 degrees. So you're going to go all the way around that 336-sided figure, but it takes 36 of them, so they're only 10 degrees apiece. The interior then has to be 170. So we can take 170 times 36, and that will sum them all up to 6120. But notice we could have also used this formula, 180 times 34, and that will always work, 6120. All right, so let's move on to number 6 down here. Let's get us some space first. So number 6, here we have the radius, and we're talking about the radius of a circumscribed circle. A is apithom, so let's look at this pentagon on number 6. Yeah, it looks almost perfect right there. All right, so this is saying that the radius, we don't know what the radius is, but the apithom is a 12. And that's all we have. So we need the side length over here, and then we need the perimeter and the area. Well, it all boils down to this right triangle that we just created here. The apithom, or this internal radius, and then the external radius going out to this point of a circumscribed circle. Well, yeah, we need that angle, and we get that it is, well, we knew a central angle was 72, so half of that is a 36. So we actually have this triangle right here with a 36 degrees and a 12 and an R, and then I'm going to call this X, and then we'll double it to get the side length. So we get cosine of 36 degrees. Is that going to help us get one of them? Yeah, 12 over R. That will help us to get R. Let's punch this in. We get 12. R is going to be 12 divided by the cosine of 36. Let's go ahead and punch that in right now. 12 divided by cosine of 36. And we get 14.83. Let's write that out. 14.83. That's inches. Yeah, certainly will be in inches. The side length. So on X, we could do tangent of 36 equals X over 12. So if we take 12 times the tangent of 36, we get 12 times the tangent of 36. And what does that equal? 8.7. So X is 8.7. X is 8.7 something. Now if we take 8.7, we've got to double it. So that's just this guy right here. So we've got to double it to get the side length. So let's go ahead and do that. Times it by 2. Keep all those decimal places. And we get 17.43. 17.44. So the side length is about 17.44 inches. Okay, the perimeter. Well, if we take the side length and now we times it by 5, yeah, times by 5, and we get 87.19. 87.19 inches. Now the area, how are we going to do area? Well, if we look at this, we've got the area of a triangle, and then we just simply have 5 of those triangles. So let's do the area of a triangle here. When we have 1/2 times 12 times 17.44 times 5, notice that we already did that to get the perimeter. And so that's perfectly fine. If you'd like to use a perimeter, you can. But note that for our calculations in our calculator, I already have this thing. So I'm going to times now by 6, and we'll be all good. 523.11, 523.11, and that's inches squared for area. Good. Let's do this next one. Number 7 is a triangle, so I'm going to draw it kind of big, and it's a regular triangle, which means equilateral. So if we have this guy right here, and we have a radius of 8 feet, we need to find out how big this apithom is and how big the side length is, and the perimeter, and so on and so forth. So with this, we know that a triangle, the central angle, is going to be 120. So if we cut it in half, this is a 60. And you're like, oh, wait a second, this is a 60, 30, 90 triangle. See, and notice it says this, for the triangle and the hexagon, keep the answers exact. And this is why they wanted it exact, is we know a 60, 30, 90 triangle. The hypotenuse is double of the short side. So this short side's a 4. So that apithom is a 4 feet. Now the side length, let me see, we've got to do 4. This is 30, 60, 90 pattern is a 4 square roots of 3. So then this side is a 4 square roots of 3. So the side length is 8 square roots of 3 feet. Good. So the perimeter, we take this and times it by 8 square roots of 3, 8 square roots of 3, 8 square roots of 3, and we get 24 square roots of 3 feet. So again, finding the area of the whole thing, if we did 1/2 times the height, 4, times the base, 8 square roots of 3, times the number of sides, 3. Notice that here we already did that, 24 square roots of 3, and now we've got to times by 1/2 and 4, so timesing by 2, and we get 48 square roots of 3 feet squared. All right, good. Number 8. It's going to be a decagon, and all I'm going to do is do maybe something that looks like that. And just realize that here, we're headed down to the center, somewhere down here. Okay, that looks a little ski-wampus, but that's kind of what we're doing. So we're just going to be dealing with one of these triangles right now, and let's see what we get. So a decagon, first of all, the central angle is 360 divided by 10 is 36. So each one of these guys is going to be 18 degrees. So the radius is 12 meters. So I'm going to put a little x there and a little a there. So let's write this out here. Cosine of 18 degrees is going to be a over 12. We can do that. Flip that up there and that one down there. No, just 12 times the cosine of 18 will give us 12 times the cosine of 18 gives us 11.41. So the apithom is 11.41 meters. That's nice. Let's write that down. A equals 11.41. All right, can we get x? Sure we can. We use sine this time. Sine of 18 equals x over 12. Let's plug that in the calculator and get our x. 12 times the sine of 18, and this should be a much shorter number, much smaller. 3.7, so the side length is going to be double that, 2. So that's the side length, which is 7.42. 7.42 meters. Now the perimeter, remember we now have the side length, which is 7.42, and we have 10 of those sides. So we take that guy and times it by 10, and that gives us 74.2. Well, I knew that. I could have done that without the calculator. So the area. Now again, let's look at what the area is. We're going to take 1/2 the side length, which is 7.42, times the height, which is a 12. I'm going to put this guy right over here. 1/2 times 12 times that. That gives us the area of one triangle, 1/2 base times height. And then we're going to times that by the number of triangles we have. So we're going to do that and do it over here, and then in 10 of them to get the whole area of the polygon. Notice that we already have that as the perimeter. And so 1/2, 12 times perimeter. So 6 times perimeter, we can do that in the calculator, times by 6. And what do we get? 444.98. 444.98. And this will be meters squared because we're now in an area. Good. Okay, number 9, the hexagon. Let's see if we can draw it nicely here. Close enough. Okay, so we have here that the side length is length 10. So if we go like this and then cut that guy. Now remember, this guy is a 60-degree angle in here, so we have a 60, 60, 60. Yeah, so when we do this, notice we have a 30, 60, 90 triangle, which is why the hexagon says to keep the answers exact. So we're going to end up with square roots of 3 again somewhere. So this is a 5, and the 30, 60, 90 shortcut, this is a 10, and this is 5 square roots of 3. So let's write that out. The radius is a 10 centimeters, and the apithom, some people call it an apothum, but I think it's apithom, is 5 square roots of 3. And that's there. Good. So the perimeter is 10 times 6. That's going to be 60 centimeters. And the area of it, let's walk through it one more time, equals 1/2 times 5 square roots of 3 times 10. So this is the area of one triangle times the number of triangles. So let me put that in. That's one triangle and number of sides. Now notice that these guys right here, if we times these two together first, that's the perimeter and it's already there. So the perimeter, 60, times 1/2 is 30, times 5 square roots of 3 would be 150 square roots of 3 centimeters. And it was all done exactly without the calculator at all. All right, next one. Number 10, a 24-sided polygon. Yeah, I'm going to draw like 3 of the sides because it's going to be really tough. Now, we should note that it goes way down here. Okay, so with 24 sides, what do we have? We have 24-sided polygon. The apithom is 6 kilometers. All right, so let's figure out these angles first of all. We know that the central angle is 360 divided by 24. That's the central angle is 15. So when we divide that in half, we have a 7.5 degree. Wow. I'm going to call this R, call that X for right now. That's 7.5 degrees. That's teeny, but we can get it. We get cosine of, let's write it over here just a little bit, cosine of 7.5 degrees equals the adjacent 6 over the hypotenuse R. There we go. So R will go up there, and so R is going to equal 6 divided by the cosine of 7.5. 6.05. So this is the radius, 6.05. And you'll notice that the more sides you have, the closer these two numbers get to each other. So let's find X. Tangent of 7.5 equals, we could use sine and use it with this new 6.05 kilometers, but using that number that we have might be a little bit better for us. So tangent of 7.5 equals X over 6 times 6 up there, and we get that X is 6 times the tangent of 7.5. Ooh, that's really short. So X is 0.7899. Now remember, that's only half of the side, so we got to times by 2, and this is the side length, 1.58. So the side length is 1.58 kilometers. Yeah, this was 0.7, and so we had to double it to get the entire side length, 1.58. All right, once we have that, we need the perimeter, so we've got 24 of those sides times by 24, and that's, 37.9. And then the area, let's write it out one more time to see all of it. The area is 1/2 the height of the triangle times the base of the triangle. There we go, 1.58. That's the area of one triangle times 24. Well, we've already done that. That's the perimeter. Now we just need to times by 6 and 1/2, so that's timesing by 3. And we get 113.7. 113.7, and now this is an area, this is kilometers squared. Cool. Number 11, it says find the probability of an object falling inside a circle of radius 8, but outside an inscribed regular triangle. So if we have a triangle right here and we have a circle, okay, that's kind of an ellipse, or that's, never mind, I don't know what that is. But you've got a radius of 8, and we need to find the probability of an object falling out here, but outside the inscribed triangle, but inside the circle. So yeah, we're going to be taking the area of this shaded thing over the pi r squared. So we got to find this area of this triangle and subtract it out. So let's go ahead, and this is a triangle, so we can keep everything exactly, well, exact. So this is going to be a 60, so a 30, 60, 90 triangle. That's going to be 4, and that's 4 square roots of 3. So the side length is 8 square roots of 3. So the area of this triangle is going to be 1/2 times 4 times 8 square roots of 3 times 3. So the perimeter, oh hey, we just did this problem number 7 right up here. Oh my word. Look, but we got the same thing. 24 times 2, that's 48 square roots of 3. That's the area of the triangle. So if we take the whole circle minus the triangle, we get, this is pi 8 squared, so 64 pi, minus the triangle, which is 48 square roots of 3. It equals the area that we're looking for right here. Let's plug that in and get a decimal. 64 pi minus 48 times the square root of 3. Square roots of 3. And we get 117.92. That is this area right here. Now to get a probability, we need that part over the total, which is the whole circle. So 64 pi. What does that equal? Divide this by 64. Ooh, we better put parentheses on that guy. 64 times pi. Got to make sure that 64 pi is all in the denominator. And it equals 0.586, 0.587. So a 58.7% chance, once it's inside the circle, there's a 58.75% chance that it will be outside of that triangle. Cool. Number 12, find the probability of an object falling outside of a circle of radius 11, but inside a circumscribed square. So we have a circle here, and then we have a square, oh boy, like that. So the radius is 11 here. Alrighty, so notice that's the apithom of the square. Well, this is kind of interesting. A square is nice. Now we could connect up there and do a 45-degree angle and everything there, but we have some other options here. If this is 11, then the whole square has side length 22. So if we're trying to find the probability of being out in these corner areas, then we've got to take the area of the square, which is going to be 22 squared. That's 484. We're going to subtract off the area of the circle, which is pi times 11 squared. Yeah, I don't know what that is exactly. 121 pi. That's what it is. And then we'll put that over the 484. So let's punch that in. 484 minus 121 pi, and that equals, so the area that we're interested in is 103.867. Cool. That is, let's write that out, 103.87. That is the area right out here that is not inside the circle. And we have to, for the probability, we have to divide by that 484, the total area of the whole square. So let's do that, divided by 484, enter. And we get 0.2146, 0.2115. There we go. So 21.5%. Okay, and there you have the beginning of polygons.